So Douglas is going to start his last lecture. And okay.
Okay, thanks.
So,
Here we go. Let's see if this is going to work. Okay, great. Okay, so this lecture is going to be slightly different. If I can get this thing out of the way. Okay. So the first one back in June was kind of a historical account of space-time wormholes and some of the puzzles that they're associated with. Tuesday this week was a more recent look at some constructions of wormhole solutions and applications of them, like the eternal traversable wormhole and the double cone, where they seem to mean something kind of interesting. And another notable example of that are the replica wormholes that have been used to compute the page curve. We did discuss that a little bit back in June, but not too much on Tuesday. Anyhow, what we're going to do today is something kind of continue this progression. We're going to talk about something like a topic of current research. I'm going to talk basically about a paper with these folks, Phil Saad, Steve Schenker, and Chunyu Yao, from a little less than a year ago. And this paper is aimed at one of the conceptual puzzles that we discussed back in June, called the factorization problem. So we're basically going to go through that paper and do some of the calculations and look at some of the details. So there's a piece of background that's going to be useful, two pieces of background. And the first one is what the SYK model is. So this is a quantum mechanical system. It's a concrete quantum mechanical system, or more precisely, it's an ensemble of concrete quantum mechanical systems, where we take the Hamiltonian to be the following thing: sum over an ordered set of 4 indices that run from 1 to n of some random coupling, J, A, B, C, D. So this is a random number times a product of 4 Majorana fermion operators. So these are Majorana fermions in quantum mechanics, which means just operators psi A that satisfy this this anti-commutation relation. So the Hamiltonian is just a sum of all possible terms with product of 4 fermions, so all possible 4 fermion interactions, and you add them all together with random coefficients J, A, B, C, D. So the ensemble of quantum systems with different values of these coefficients kind of defines the full SYK model. And so this is the Hamiltonian formalism description of the SYK model. And the path integral formalism, you have a path integral over these Majorana fermion fields, so over Grassmann valued functions of time. So fermions psi A as a function of time, path integral over those things. And that path integral can be kind of rewritten in terms of a path integral over collective fields, where G of T1, T, and T2 is equal to 1 over n times the sum from A equals 1 to n of psi A of T1, psi A of T2. So so here we have psi without the hat, which means that these are the path integral fields. And this collective field G is equal to the average bilinear of the fermions. It depends on 2 times because we have 2 fermions appearing. So there's this field, and there's another field called sigma of T1 and T2. And sigma is a Lagrange multiplier that enforces this constraint. So this is a constraint that defines G, and sigma is a Lagrange multiplier that enforces that constraint. So after you introduce these fields, you can actually integrate out the fermions. And so you have a description just in terms of G and sigma. And at low energies, this G and sigma description actually reduces to JT gravity. So that's the connection between the SYK model and two-dimensional gravity. It's a type of holographic correspondence where you can actually derive the mapping precisely. You can show that the action for the G and sigma fields becomes the action of JT gravity. So that's one piece of background. That's just to have in mind if you haven't seen the SYK model before. These are the main facts about it that will be useful. So the second piece of background is something that we discussed back in June. I just want to review it briefly. And this is the factorization puzzle for Euclidean wormholes. And this was discussed in a beautiful paper. Well, it's discussed in many places, but especially in a beautiful paper by Maldacena and Maus from 2007. So here's the setting. Let's imagine that Z is some boundary partition function. Like, let's say it's the partition function of the boundary theory on the topology of like a sphere times time, or some sphere, or hyperbolic space times time, or some particular boundary manifold that we evaluate the boundary field theory on. So Z is just some partition function of the boundary field theory on that manifold. So it's some number. Z is some number. And B is the evaluation. B is a kind of it's a function or functional. It means that we evaluate something in the dual gravity theory. So just notation will be easier to explain if we just do an example. So B of Z would say the following. We take the boundary manifold that we're supposed to evaluate the partition function Z on here. So I'll call that X. So we could call this ZX. But I'll leave the X off. Anyhow, this is we put the boundary manifold that we're supposed to evaluate the partition function on. So for example, this could be S1 in the drawing that I drew, but it could be some higher dimensional manifold. And then to evaluate B of Z, what we do is we consider gravity problem with that boundary condition, and we try to fill it in some way and do the path integral over the bulk gravity fields. So this is the idea of the function B. It's evaluation of this quantity using the bulk theory, using the holographic theory. Okay. Now here's the factorization puzzle. If we consider B of Z left times Z right, then we take, so Z left and Z right, or the subscripts left and right, are just to differentiate the two different copies of this partition function. They're otherwise identical. We're supposed to take two copies of this boundary condition, and then we can have, of course, fill it in this way. We could fill the boundary condition in like this, or we could fill it in with a wormhole connecting the two. And in the case where we fill it in, so we should take the sum of these contributions. And this is not equal to B of Z left times B of Z right, because in B with just one copy of the partition function, you don't have any wormholes. Whereas when B acts on two copies of the partition function, we assume that you can have wormholes. So this is a problem because Z is just supposed to be some number, and Z left times Z right should have some well-defined value. And you should be able to calculate it in the bulk theory if you want. And you should be able to calculate it either by computing the bulk answer for Z left times Z right, or the bulk answer for Z left and just multiplying it by the bulk answer for Z right. And the wormhole appears to be inconsistent with that basic fact of the boundary theory. So this is the factorization puzzle, and it's a deep problem associated to space-time wormholes. Okay, so that's the second piece of background. Now let's start our investigation today. So in some cases, the gravity theory that we're discussing is dual not to a specific quantum system, it's dual to an ensemble average of boundary theories. So I say in some cases, but there actually aren't that many cases where this is understood. Basically, it's understood that this happens in SYK, where we have an ensemble of boundary theories determined by these couplings. And it's really the average over those things that is most precisely related to the G and sigma theory and to the bulk theory. So SYK is one example where the quote gravity theory, which is the G and sigma theory, the collective field description, is actually a description of the average over couplings of something. Okay, so that's one example. And the other example is JT gravity, which we mentioned last time but didn't prove, is dual to a matrix integral, to an ensemble average of Hamiltonians drawn from a integral over random matrices. So in those cases where the gravity theory is dual to an ensemble, this is okay. There's actually no factorization problem. And the reason is that in this case, B of some partition function corresponds to the average over the ensemble of boundary theories. So let's say for the SYK model, for example, the integral over couplings, maybe I'll draw two cases. So this would be, corresponds to the average of some partition function over the family of couplings. So this would be for SYK. Or for example, to the integral over Hamiltonians weighted by some factor associated to the matrix integral times trace e to the minus beta h. So this would be for JT. So in these cases, the evaluation in the bulk theory actually corresponds to an ensemble average in the boundary theory. And in those cases, of course, it's perfectly fine to have an equation like Z. This non-factorization condition is perfectly fine. In fact, the difference between these terms, the average of the product and the product of the averages, just gives the variance of the partition function in the ensemble of couplings, the ensemble of random matrices. So for these kinds of weird cases, this is okay. This non-factorization is okay, and there's no problem with including wormholes. But you could ask, many people ask, it's a very natural question, what if we study one of these examples, SYK model, JT gravity, or whatever, even one of these favorable examples where the wormholes seem to make sense? What if we pick one of these examples and we just pick just one theory from the ensemble? Rather than averaging over the couplings or averaging over the Hamiltonians, what if we just focus on one particular choice of these couplings, J, A, B, C, D? So what happens if we freeze the SYK couplings to some specific values? Then we have a honest quantum mechanical system where the partition function just takes some value. It doesn't have a probability distribution, it doesn't have a variance. And the question is, in this case, what happens to the wormholes? So do the wormholes still exist? How is factorization restored when this ensemble average here kind of collapses to just a single term? Okay, so that's the question that we want to analyze. Any questions about this motivation or the background?
Can I ask one question?
Yeah.
So I'm just a bit confused by the second point. So I thought, but maybe I just misunderstood, I thought that JT was the bulk dual of SYK, but here it seems that you're presenting it as also some boundary theory, or maybe I'm just misunderstanding what's written.
You mean why did I list these as two separate examples?
Yes.
Yeah, good point. So just to emphasize the question here, I said that at low energies, this description reduces to JT gravity. So that's like SYK equals JT. And now later, a couple minutes later, I'm talking about them as though they're two different examples. And that's because the relationship between SYK and JT gravity is an approximate relationship at low energies. And even there, it's only approximate. But there's a precise relationship between JT gravity. There's an exact relationship between JT gravity and an ensemble of random matrices, and an approximate relationship between JT gravity and SYK. So let me try to write, so there's some exact kind of averaged duality between JT and an ensemble of random matrices, integral over matrices weighted by e to the minus the rank of the matrix times some potential. So this is one exact duality, and another exact duality is between SYK. Sorry, let me rewrite it this way. Let me write it as SYK is on the right-hand side now. SYK is on the right-hand side, and on the left-hand side, we have the G and sigma theory. So here are two exact dualities between sort of an average, I should say average SYK averaged over the couplings and the G sigma theory. So these are exact dualities, exact statements. And then there's a further approximate statement, which is that these things, let me draw in a different color. These things are kind of approximately equal to each other at low energies. And that's not an exact statement. To check that it's not an exact statement, we can look at the right-hand side and notice that SYK is not exactly equal to an integral, to a random matrix integral. It's a little bit more structured. The Hamiltonian is not a kind of an unstructured random matrix. It's one which is built out of 4 fermion interactions. It's a kind of random matrix, but it's a sparse random matrix. It's not a traditional random matrix in this sense. So these two systems are not exactly equal to each other. They're approximately equal to each other, and the approximation is good enough that you can make sense of the wormholes, in some cases in JT gravity, as describing solutions of the G and sigma theory and reproducing physical effects in SYK. A notable example of that is the eternal traversable wormhole discussed by Maldacena and Chi.
Okay, thank you.
Yeah, thank you for the question. So I'm really glad you asked it, because this was pretty unclear. Okay, any other questions about this? Or okay, so let's get going then. So here's the summary of our results, and you're going to find this ridiculous, but we're going to work in a simpler model. So I love toy models. Not everybody does, but I do. And we're going to work in a model that's even simpler than SYK. So SYK is a kind of a toy model of quantum mechanical systems, and we're going to work in a toy model of SYK. So that's pretty bad or pretty fun, depending on your perspective. But within this model, it's simple enough that we can analyze it very well, and we find the following features. So first, well, there's sort of 3 slogans. The first slogan is that wormholes persist. So what this means is, even once we freeze the couplings, once we fix the couplings to specific values, the wormholes persist. That means that they still exist and still contribute in the theory with fixed couplings. So that appears to create a paradox, the factorization puzzle that we just discussed, that wormholes would break factorization in a theory with fixed couplings. So how can it be? How can this be? And the answer to that has to do with the next part, which is that in the theory with fixed couplings, there are further solutions. There are further semi-classical configurations that we refer to as half-wormholes. That might be a better name. I'm sure there's a better name, but this is a good enough name for now. So the half-wormholes do not exist in the average over couplings. When we average over couplings, you don't have the half-wormholes. But when you fix the couplings, you do have these half-wormholes. And they combine with the wormholes to restore factorization. So the factorization puzzle is resolved by including the wormholes. That gets you into trouble, but then also adding these new configurations, the half-wormholes. So that's kind of the thing that comes in to save the day. And the third point is a little bit more abstract. we'll discuss it if we have time, that there are kind of multiple ways to describe multiple different collective field descriptions. So if we're trying to compute ZR times ZL, then we have a choice. One legal computation is to compute ZR and compute ZL completely separately, just to two different computations, each with their own individual collective field description. The other possibility is to do a simultaneous computation of ZL times ZL times ZR, and then we have collective field variables that represent wormholes connecting them. And both descriptions are correct, and they're simultaneously possible because of the half-wormholes and the interplay with the wormholes. So that's the basic summary. So now we're going to go through that statement in a tiny bit of detail now, and then we'll go over it in more detail later with actual equations. So let's start by first discussing what do we mean by wormholes and half-wormholes in SYK, or as we'll see in a second, an even simpler version of SYK. So let's imagine computing z left times z right in SYK, so two thermal partition functions. That means we put the boundary theory, the quantum mechanics, on a circle. Trace of e to the minus beta h is a path integral on a circle. So we have one circle for the left quantum mechanical system and one circle for the right quantum mechanical system. So that's what we've drawn here, these two circles. And we can have a collective field description of the fermions on these two circles in terms of the bilinears of the fermions. So I remind you the formula that we wrote before. G of T1, T2 is equal to 1 over n times the sum over A of psi A of T1 times psi A of T2. So it's a bilinear, it's an average bilinear of the fermions averaged over the different flavors of fermions, and different flavors of fermions in the SYK model. Okay, so if we consider a system like this where we have these two separate boundaries, then obviously we can have collective fields that will write with indices G left left, which represent bilinears of the fermions on just the left boundary and left boundary at two different times. And of course we can have G right right, which are collective fields that are built out of a bilinear of fermions on the right boundary. But we could also consider collective fields G left right, with built out of a bilinear fermion psi A on the left system times psi A on the right system, summed over A. So we can have these different types of collective fields. So here we have G left left, G right right, and G left right. And similarly, we have sigma left left, sigma right right, and sigma left right, the Lagrange multipliers that enforce these constraints. And a wormhole is a configuration is a solution where G left right and sigma left right are not equal to 0. So it's like there's a large degree of correlation between the left and the right boundaries, and making this variable non-zero is analogous to having a geometrical connection, having a wormhole connecting the two boundaries. So this is our definition in SYK language, in G and sigma language, of what a wormhole is. Okay, does this make sense? Does this seem like a reasonable criterion? Well, I hope it seems reasonable enough. One thing that I want to get out of the way now is that for clarity and ease of presentation, in most of the rest of the talk, we're going to focus on this variable sigma. We're going to focus on the variable sigma instead of G. So we're going to draw plots and consider functions of sigma and not of G. And we're going to say that it's a wormhole if sigma is non-zero, instead of saying G is non-zero. And your intuition for sigma might not be as good as the intuition for G, because I've kind of defined G as this bilinear, and sigma seems a little bit stranger. It's this Lagrange multiplier that enforces the constraint. But on a saddle point configuration, a classical solution, sigma and G are related to each other. So if one is non-zero, the other is non-zero. And if one is big, the other is also big. So G and sigma are not too different from each other. And sigma is just a little bit easier to work with, a little bit more convenient to work with. So I hope this won't bother you too much. So, okay, so we've defined, so we're trying to give a little more detail about the statement that the wormholes still exist, and that half wormholes exist, and so on. So here's the kind of mathematical statement of what that means. Let's imagine that sigma, which is really a function of 2 times, let's imagine that it's just a function of no times, just a single variable. That will be true in a simple model we discussed. So rather than thinking of sigma of T1 and T2, just think of a variable sigma. Okay, we'll explain why that's true in a second in the model we're going to discuss. But okay, and then let's imagine integrating over that variable. So we're integrating over that variable, and here's the integration space. This is the sigma plane. So the complex sigma plane. We're supposed to integrate sigma over some contour in this plane. And let me draw a few things in the plane. So there are some solutions where sigma is complex and non-zero. It happens that there are 4 of them, symmetrically distributed in the complex plane. These are the wormhole solutions. So what that means precisely is that if we average over the couplings, then there are solutions for these collective field variables at these non-zero values in the complex plane. So these red points correspond to classical solutions of this theory, which are wormholes, because sigma is non-zero. So by definition, these correspond to wormholes. Now, that's the whole story. If we average over the couplings, there's just these 4 solutions, and that gives some wormhole contributions. But if we don't average over the couplings, something interesting happens, and here's what happens. There's a region kind of reasonably close to the origin where the action for sigma is not self-averaging. What that means is that the action for sigma, the function that we're actually supposed to integrate here, depends strongly on the choice of couplings. And in that situation, whether we're averaging over the couplings or whether we're not averaging over the couplings makes a really big difference, because the function that we're supposed to be integrating depends on the couplings. Outside this region, the action is self-averaging. And that means that outside this region, it doesn't really matter if we fix the couplings or if we freeze them to some particular value. And notice that the wormhole solutions lie outside this region. They lie outside this shaded purple region. And that means that the wormhole solutions are in the self-averaging region. So for the perspective of these solutions, it doesn't matter whether you're integrating over the couplings or whether you're freezing them. And that's the statement that the wormholes survive in the theory with fixed couplings. They basically just don't care whether you fix the couplings or whether you're averaging over them. And they don't care because of this mathematical fact that the action is self-averaging in that region. Okay, so what about inside the purple region? Inside the purple region, the action is not self-averaging, so there can be a big difference between the average theory and the non-average theory. And what happens is that there's actually a really big contribution to the integral from the origin itself. So in the theory with fixed couplings, there's a big contribution from the origin, and this contribution we call a half wormhole. And it only exists in the theory with fixed couplings. If you average over the couplings, its contribution averages to 0, and the integrand vanishes at the origin. But if you don't average over couplings, then there's a huge contribution at the origin, and it just depends sensitively on precisely what the values of the couplings are. So it's this picture in the complex sigma plane that is the whole story. This picture summarizes both the fact that the wormholes survive and also that we have these new contributions, these half wormholes in the case with where we fix the couplings. Okay, so that's the
So Douglas, maybe I would like to ask something.
Yep.
If you could clarify a little bit more why these collective fields are relevant when the couplings are fixed. To me, it's really not obvious. I fully understand why we introduce them and why they're relevant when you average over couplings, because, you know, like the G, for example, is this sum over psi A. So you sum over all these indices, and that's related to the fact that when you average over couplings, you have these symmetries sort of. So these invariant bilinears are relevant, and that's the usual, you know, large N technique. So all this is clear, I think, for probably everybody. But why are these objects still playing any role whatsoever in a model where you wouldn't average, and then all these indices, you know, you don't have any symmetries, etc., etc.
Yeah. So why are they a useful description even in the theory where you don't average? That's kind of the question you're asking. Why? Are they
what are they good for? And
yeah, what are they good for? So good question. Well, your question could be two things. So one aspect of it is it even legal to use a collective field description without averaging? Like, is it mathematically allowed? Forget about whether it's useful or not. Is it actually possible? And well, the answer is yes, you can do it if you want. The penalty is that the action for the collective fields is very complicated. Depends in general on the couplings. But, and this gets to why it's useful, there are regions of the complex plane. So the region outside this purple region, where the action is basically the same for the averaged and non-averaged theory. So you get back essentially the familiar G sigma action of the average theory in part of the integration space. And so that means that you're able, using the familiar G and sigma theory, you're able to analyze part of the problem. You're able to control the contributions of these wormholes, and the complication of using these of not averaging is the fact that you have this new region that you have to deal with.
Probably what I cannot really see is how, well, it's technical probably, is how do you analyze the effective action in terms of these collective fields when the coupling is fixed, and how can you see those things? So this is very puzzling to me. So that's
good, great. I'm good. I'm glad you're asking the question, because that's what we're going to do. That's basically the rest of the plan for today, is to actually go through that in detail for a simple model of SYK. So I think that you will have your questions answered in the rest of the talk. But if at any point you're uncomfortable with what's going on, or you have a particular aspect of the question that is not being answered, then ask it, and I'll try to give a more specific answer. But basically, we're going to try to answer your question in the rest of the time. Okay, actually, I lied slightly. I want to give one more vague picture, and then we'll actually get down to the nuts and bolts, of answering this question. So here's the bulk picture that is useful to have in mind in the theory with fixed couplings. So here are some wormhole pictures that are supposed to represent the situation in the SYK model with fixed couplings. So suppose we're computing z left, z right all together, doing the bulk computation of z left, z right all together with fixed couplings. Then here we have the following kinds of contributions. We can have a completely factorized non-wormhole contribution, like two separate black holes. That's this first term, where the x means that it's slightly dependent on the couplings. The x means a small dependence on the couplings. We can also have a wormhole like this, as we've just argued. Even with fixed couplings, the wormhole survives, but it has some very small dependence on the couplings. The x's are not too important. But The claim is that we can have new configurations. We can have a disk, like a black hole geometry on one side, and a half wormhole. So this thing with a jagged red boundary here is a cartoon of a half wormhole. It's a kind of a new configuration that you need to include in the theory with fixed couplings. So you can have a black hole times a half wormhole, you can have a half wormhole times a black hole, and you can have two half wormholes. Okay, and the red line linking the two half wormhole boundaries there is reminding us that these are half wormholes in the theory where we're computing z left and z right simultaneously. Okay, so now what if we do a separate computation? We do a computation of z left and z right completely separately, then we just get a square of this computation of a black hole plus a half wormhole. There's no wormholes possible in this theory. And if you expand out these terms, you get 4 terms now instead of the 5 terms on the previous slide, and they agree with each other because of an identity that says that the half wormholes that are linked half wormholes, that is the half wormholes in the first type of theory, where we're computing z left and z right simultaneously, the half wormholes in that theory plus the ordinary wormhole are equal to the half wormhole in the theory where z left and z right have nothing to do with each other. So this is the identity that restores factorization. If we remove the half wormholes from this identity, from the two sides, if we erase these terms, then we get an identity that is false. It says wormhole equals 0. That's the kind of the factorization puzzle. It says the wormhole is an obstacle to factorization. And in this theory, the obstacle goes away because you add these half wormhole contributions to both sides, and they fix it up. Okay.
Sorry, can I ask? I think I missed. So this last identity, what is the first term? What is the red line connecting them?
Yeah, the red line is saying that this is a notation to say that these are half wormholes in the theory where we're computing z left times z right simultaneously. So there's 2 slightly different bulk theories. There's a theory where we're computing z left times z right simultaneously, and there's a theory where we're computing z left by itself and then later computing z right in a separate computation. Both of those theories have half wormhole contributions, but they are slightly different. The contributions of those half wormholes are slightly different. And so we use the notation with a line between them to indicate the half wormholes in the first kind of theory, and no line to indicate the half wormholes in the second kind of theory. And they are related by this equation.
And is this equation supposed to be obvious, or is...
No, okay. This is a it's not obvious, and it's a non-trivial fact that rescues factorization. So the main point that I want to make here, because I haven't proven this equation to you, the main point I want to make is that the thing that saves factorization is a kind of non-trivial equation relating half wormholes in 2 slightly different theories. So it's really about the half wormholes that restores the factorization. I hope it's clear from what I've written here that if this equation is true, then these are equal to each other. So we have no factorization problem. So that's all I want you to be able to follow on the slide, is that if this equation is true, then these 2 things will be equal to each other. And I claim that these things are true, and that saves factorization.
Okay, then I have another question. So these half wormholes, what are we supposed to think about them? Like, is this some completion in the bulk that is not smooth, or how different is it from just the completion that one usually does?
Yeah,
it doesn't have any.
We don't know what they look like in the bulk theory. Sorry, let me try to answer it in a better way. This analysis is a precise analysis in the SYK model, or in a relative of the SYK model. And the pictures I'm drawing here are an attempt to translate that into expectations for a more conventional holographic theory. We don't actually know how it works in a more conventional holographic theory. We don't have the same precise control that we do in the SYK model. So these cartoons are supposed to motivate somebody to work out really what these configurations are. Now, it's a little bit better than that. It's a little bit better than that because what you can show using the SYK model is that the pattern of correlation. So let's look at one of these half wormholes. So I draw it kind of like this with a jagged line here. The pattern of correlation on the boundary of this theory, so the correlation between an operator here and an operator there, so the pattern of correlation on the boundary of this geometry, that is the same pattern of correlation as in a wormhole geometry, where you restrict attention to just correlations on one boundary. So this is the sense in which, this is why we call it a half wormhole. It's because the pattern of correlation on the boundary looks the same as the pattern of correlation on a wormhole geometry, just restricted to one of the boundaries. So I believe that that means that in the bulk, we should be looking for a configuration that is geometrically similar to half of a wormhole, because it's the geometry of the bulk that determines the correlation on the boundary. And if the correlation on the boundary looks the same as on a wormhole geometry, then the bulk geometry should also look the same as on the wormhole geometry up to a certain point. And that point we just draw with this squiggly red line here, and I have no idea what is happening there or where that is in the bulk. There was an interesting suggestion by Yiming Chen and Juan Maldacena that maybe the half wormhole jagged line should be the actual singularity of the black hole. So maybe the half wormhole is a geometry that kind of ends at the singularity, a wormhole geometry that ends at the singularity at r equals 0 of a black hole. That's a very interesting suggestion. I don't know if it's true. I don't know if it's true or not, but the squiggly red line here is supposed to capture, kind of represent our ignorance. The thing that we actually know is that the geometry kind of closer to the boundary should look like part of a wormhole geometry.
So precisely, if you look, for example, at the sigma RR, you're saying that it's the same in the half wormhole than in the wormhole, but then the sigma LR is like 0 in one and non-zero in the other.
Exactly. Yeah, exactly.
Okay,
precisely.
Thank you.
Yeah. Okay. So so let's now get to the nuts and bolts. Let's go through some of this in some detail. So let's first explain what is the model that we're going to be discussing. The model is like the SYK model, but it's simpler. So it's SYK model where you take the path integral and you just restrict it to one instant in time. So it's not a path integral anymore. It's just an ordinary integral over the fields at one time of the original SYK model. This doesn't have a nice Hilbert space interpretation, at least not one that I know of. So it's just a theory that's defined by a path integral, but it's actually an ordinary. So it's just an integral over n Grassmann numbers, not Grassmann valued fields, just Grassmann numbers of the following thing: exponential of j a b c d times psi a, psi b, psi c, psi d. So, and here the summation is over a ordered sequence of A, B, C, and D running from 1 to n. So this is the interaction term of the SYK model, but here we have it at only just one instant of time. The whole theory is just at one instant of time. Okay, so this is the model, and now we're going to analyze it. First, we're going to review the analysis of the average theory. So we're going to review kind of in this model how the average theory looks and how we get this G and sigma representation. Then we're going to do the same thing without averaging over the couplings. So what does the average mean? Average of Z over J would be an integral dj of some Gaussian times j abcd squared of Z as a function of J. So I should write this Z here as a function of J, but let me not complicate the notation. So this would be the average over J. And actually, it's easy to show that that is 0. So the average of Z is equal to 0. So it's exactly equal to 0 if we average it over J. So Z is not an interesting thing to study in the average theory. The first kind of interesting quantity we can study in the average theory is Z squared, the average of Z squared. So Z is a real quantity, and we can study Z squared. And you should think of this as Z left times Z right, where we just label the two factors as left and right. So so let's see how we can compute that. So to compute the average of Z squared, we would take 2 copies of this thing here, take 2 copies of this, and then we would average it over, integrate it over J with a Gaussian measure for the J couplings. And you know what happens when you do a Gaussian integral with something e to the J times something, you get that thing squared. So Gaussian integral formula will take whatever J multiplies and we'll square it. So what does J multiply? Well, it multiplies some A, B, psi A, psi B, psi C, psi D, which I'll write as psi A, B, C, D for the left system, plus multiplies something psi A, B, C, D for the right system. And in the original action before integrating, we have that thing times J. After integrating over J, we're going to get this thing squared, right? And we can expand that square out, and we'll get a term involving the left fermions times the left fermions. That vanishes because Grassmann numbers square to 0. And then we'll have a term involving the left fermions and the right fermions. So the fermions from the two different copies of the partition function. And that doesn't vanish. And that's the remaining term we have to write. So let me write that here. So we get some number here times psi A, B, C, D left times psi A, B, C, D right. And this is summed over A, B, C, and D. So this is the exact formula for the average of Z squared. Okay, so you can go ahead and try to compute this in different ways. One nice thing to do first is to simplify it slightly. We can write it in the following way. Here I'm going to fix the number because this number will be important. I'm going to actually fix a numerical coefficient. We get the following thing: 1 over n times psi A left, psi A right to the 4th power. So this expression is equal to the previous expression. It's equal to the previous expression. Again, using the fact that psi squared is equal to 0. So here we've just reordered the fermions slightly and written it in this way. So, okay. Okay, so this is a nice expression for the average of Z squared. And you can go ahead and evaluate this one way or another. We're going to take a kind of a indirect approach. Well, one of the good ways of evaluating it is to introduce collective fields. Introduce these G and sigma fields. You're going to see now what this G and sigma trick is, which is very typical in studies of SYK, and will help us here as well. So how do we do it? Well, if we put a delta function that sets G, I'll call it, for the moment, I'll call it G left right, that sets G left right equal to 1 over n times psi A left, psi A right. So if we insert this delta function, then we can write the whole theory as just exponential of n over 4 times G left right to the 4th power. So this is obviously a legal rewriting of the previous expression because the delta function sets G left right equal to that fermion bilinear. And then the term we've included here is precisely the term that we had in the previous second. So just integrating over G using the delta function, it returns us to the previous expression. So to save notation, I'm going to leave off the left-right subscripts of G. In this theory, it's simple enough that there is actually no left-left field. There's no G left-left, and there's no G right-right. The only collective field we need is the kind of wormhole one. It's the one that represents correlation between the two factors. So the only G and sigma in the game are going to be the left-right ones, the wormhole ones. So I'm just going to leave the subscripts off. I hope that's not confusing. Okay. So how do we do this? How do we represent this? Well, we introduce an integral representation of that delta function. So we write that as e to the n times sigma times g minus sigma times psi a left, psi a right. And then we have this same factor. I'll just copy it. So, okay, so the first term here, if you integrate over sigma, you integrate over this sigma here, then integrate it along the parallel, along the imaginary axis. So we're integrating sigma over the imaginary axis. Then that gives this delta function here. So that just gives us a delta function that says G equal to this fermion bilinear, and then the rest of the expression reproduces what we want. Okay, so now we've rewritten things this way, and there's one final step in the G sigma procedure, which is to integrate out the fermions. Because now we've written things in a nice way where actually it's going to make life a little bit simpler. If I change where the minus sign is, this doesn't actually change the answer because delta of minus x is equal to delta of x. So the minus sign will make it more consistent with what I wrote below. Anyhow, okay, as I was saying here, the fermions enter only quadratically, psi left times psi right. So we can integrate out the fermions simply, and the integral over the fermions of this expression just gives us sigma to the power n. The integral over each pair of fermions, psi left, psi right, for each value of a, gives us a factor of sigma. And the integral over all n such pairs gives us sigma to the n. So we've written that here as e to the n times log sigma. So this part comes from integrating out the fermions. And what's left is just what we had in the previous line. So we have this term here, which we had in the previous line. We have this term here, which is the original action in terms of the fermion bilinear. Okay, so that's it. That's the G and sigma representation. And this is exact. This is this manipulation that we've done here is completely mathematically rigorous, and it's an exact rewriting of the average of z squared. And notice that there are no longer any fermions. We just have these G and sigma variables. So it's a two-dimensional integral representation of the exact answer. Okay, and you can analyze this. You can do this integral exactly. You can write an exact formula for it. But here we're interested in the behavior at large n, and there you can write a simple formula by doing a saddle point approximation of this integral. So what are the saddle point equations? So let's first vary with respect to sigma. We get the equation 1 over sigma minus g is equal to 0. So that says that sigma is equal to 1 over g. And the other equation, we have varying with respect to g says that minus sigma plus g cubed is equal to 0. So that means that altogether, we have the equation that g to the fourth is equal to 1. And similarly, sigma to the fourth is equal to 1. So we have solutions which are the fourth roots of unity for g and also for sigma. So these are the saddle points. We have 4 saddle points. And we can evaluate the action on these saddle points. Let's see, how do we evaluate that? So we have n times log of 1 plus a phase, and a phase, well, the phase, let's not worry about the phase for now. You can take that into account, but basically the first term doesn't contribute. The first term here doesn't contribute. The second two terms contribute, get minus sigma times g. So that's exponential of minus n. And then we have plus n over 4. So it's like e to the minus 3/4 n. So that is in fact the right answer for the scaling with n of this integral z squared. Is e to the minus 3/4 times n, and there's a numerical factor that you could work out by doing a one loop determinant and including also the effect of this phase and the sum over the 4 saddle points. And that numerical factor turns out to be 2. So the large n approximation for this thing is just 2 times e to the minus 3/4 times n. Okay. So that's the large n analysis of this integral. And this contribution that we have here, I emphasize, it comes from a wormhole. So in the analogy to gravity, this contribution is a wormhole because g and sigma, which are the analogs of g left right, sigma left right, so these are the left right variables, these are non-zero on the saddle point. There's a saddle point where the two replicas, the two copies of z are correlated with each other. The bilinear is non-zero, and the whole answer for z squared in this case comes from a wormhole. So, okay. I'm not sure if you're bothered by this, but you might be bothered by the fact that this integral here looks a little bit weird. Like if I try to integrate over g before doing the integral over sigma, then this is a divergent integral. So is this really completely well-defined? Well, the answer is that it's completely well-defined if you integrate over sigma first. So if you integrate sigma over the real axis, over the imaginary axis first, then it's a completely well-defined integral. And that means it's what's called conditionally convergent, where it depends on which order you do the integrals, whether it's convergent or not. We can make it a completely well-defined convergent integral by rotating the contour of this conditionally convergent integral, which is legal. And we get the following integral representation with lowercase g and lowercase sigma. They differ by a phase from capital G and sigma. We've rotated the contour. And now we integrate these things over the real axis. And we have the same action with some different factors of I and minus signs that come from the phases that we introduced in G and sigma. So I'm not going to belabor this change of variables, but this is a simple contour rotation of the previous integral. And you'll notice now that it's completely good, well-defined integral. We can integrate over G first if we want. It's a convergent integral. And we can also integrate over sigma first. So the integral is well-defined for either order of integral. Either order of integration is a completely convergent integral. Okay. So here's the summary of the computation of z squared, the average over couplings of z squared. I'm going to draw it in this, simplify it to this cartoon. So one dot represents the z system, z left system, the other dot represents the z right system. And the configuration that's important is a wormhole configuration representing correlation between the two. We'll just draw that by a line connecting them to represent the pattern of correlation. So that's the computation of z squared. Okay, so now we'll do the same thing in like 3 seconds for the computation of z to the 4th power. So this is the next interesting thing to compute, is that the average of z to the 4th power. So now we have 4 copies of the system, and we're going to label them as left, right, left prime, and right prime. There's no difference between these things. It's just to have labels associated to them. They're all exactly the same. And then we'll give each of them dots, left prime, right prime, each have their own dots. And the different kinds of configurations you can have, if you work out the collective field description for these things, is you can have a pattern of correlation like this, where left and right are correlated with each other. So that means that the G left right variable is non-zero, and the G left prime right prime variable is non-zero. But for example, G left prime is equal to 0. So that's the first kind of configuration, is a saddle point of the collective field description, where the left right and left prime right prime variables are non-zero, but the others are all 0. So that's what this first configuration represents. And by symmetry, by permutation symmetry between the different copies of Z, you can obviously have two further configurations with different patterns of correlation. So these kind of look like Wick contractions. We interpret them as different patterns of wormholes that you can have connecting the four systems together in pairs of wormholes. So this actually gives an answer that Z to the fourth is approximately equal to 3 times Z squared squared. So those are the three terms here, and that formula there is saying that the variable Z is approximately Gaussian distributed. So it's approximately a Gaussian random variable in the integral over couplings. Okay, so we're done with the average theory now. This was kind of a review of SYK techniques in the context of this simple model. And now we'll move to the non-average theory. But let me see if there are any questions about the average theory. Okay, folks are awfully quiet. I hope that it's making sense, but please don't be shy about asking questions. Okay, but let's forge on. So we will compute now the same thing. We're going to compute Z squared. You could start with Z, but we won't. We'll start with Z squared because it's what we computed a second ago. We'll try to compute Z squared in the non-average theory. So there's no more angled brackets, no integral over J. We have here a fixed set of J coupling J, A, B, C, D are fixed numbers. So we want to compute this thing here. So this is our target, is to compute this. And well, of course, we're allowed to multiply this by 1 if we want to. We're allowed to multiply it by 1. And we're going to multiply it by 1 in the following form. To multiply it by 1 in the form of an integral dg delta of g minus 1 over n psi a left psi a right times exponential of n over 4 g to the fourth minus 1 over n psi a left psi a right to the fourth power. Okay, so I hope you will agree that we multiplied the expression by 1 because the integrating over g using the delta function sets g equal to that fermion bilinear. And after doing so, these two terms cancel with each other, and and we get just exactly 1. So this was a legal step. Now, what do we do next? What we do next is we represent the delta function using an integral over sigma, just like we did before. So you notice that this looks pretty similar to what we did in the average theory. We had this delta function there. We also had this factor here. The difference just is in the fermion part of the action. That's different than in the average theory, but the g part of the action so far is exactly the same as in the average theory. Okay, so we represent the delta function using a Lagrange multiplier sigma. I'm not going to do that again. It's exactly the same steps. Let me rotate the contour again to go from these sigma and g variables to sigma and g, which are supposed to be integrated over a defining contour that's on the real axis now. So, okay, so this is what we get. And actually, let me put a third step here. Well, okay, so we get z squared is some integral d sigma dg and d2n psi of some stuff. Okay, and then we can, in principle, we can integrate out the fermions. It's more complicated this time, and you'll see the complication in a moment. But in principle, we can imagine integrating out the fermions. And for convenience, we'll also integrate out g, so that all we have left is sigma. So in principle, we can do that. And I'll just write what we get in terms of two functions that we'll discuss in a moment. Integral of psi times phi. And these things together should be thought of as e to the minus the s for sigma. So these functions, which I'll define in a second, are the result of integrating out the fermions and integrating out g. And they give us the path integral weighting, or the just ordinary integral weighting for the remaining variable, which is sigma. Okay. So let's define the functions now. So first of all, what is this capital psi? Capital psi is the result of doing the g integral. So g over 2 pi I over n of e to the n times minus I g sigma minus 1/4 g to the fourth. So where does this come from? Well, when we represent the delta function using a integral over sigma, we have some e to the n times g times sigma term. After rotating the contour, that becomes this term here. That's this term. And what else do we have? We have this thing, which is this factor here. And so those are the only two places where g appears. And so we can integrate out g to get this function psi. It's kind of an interesting function psi. I think it's what's called a Pearcey's integral. I forget exactly if that's the right name, but you should think about it as a little bit like a Gaussian. If the power 4 there was a 2, then this would be a Gaussian integral. And this integral, it behaves a little bit like a Gaussian in sigma. It actually decays less rapidly. It decays faster than exponentially in sigma, but slower than a Gaussian. It's like e to the minus sigma to the 4/3, I think. So it's a kind of a rapidly decaying function of sigma. That's what psi is. Okay, and what is phi? The other part, that phi is the thing that you get by integrating out the fermions. So this is very complicated. This is not a simple function like a Gaussian. This one is complicated, but we can write it in principle. So let me just write it down. J A B C D times psi left A B C D plus psi right A B C D plus psi left A psi right A times sigma minus n over 4 times 1 over n psi A left psi A right to the 4th power. Okay, so that's phi, and let's try to understand where these terms come from. Well, one thing is obvious. These terms here are just copied below, so those ones are easy to explain. This term here is also copied below. That's here. So that one is also easy to understand. And the final term is the one that comes from writing this delta function as an integral over sigma, using the integral representation of the delta function. And that's responsible for this term here. So, so that's what we get. So again, this is an exact rewriting of the path integral. It might not look very useful so far because we've just have this like enormously complicated function phi. So it might not look like we did something useful, but but it's mathematically legal. Okay, so let's just try to make contact with the previous average theory. So if we average the function phi over the couplings j, if we average over j, we can do that integral here. The integral over these, so the Gaussian integral over j, it squares the term that follows j in the exponent, and that term just cancels this term by construction. So we end up with this as an integral d2n psi of just e to the psi left a psi right a times sigma, and that gives us sigma to the n. So so the integral over the fermions of the average of this thing over J gives us back the sigma to the n term that we had in the average theory. So this connects us back to the derivation we did before. It's just that now we also have a formula that makes sense as a function of the couplings J. So we've kind of just delayed the average over J until later, and we have a formula that makes sense for fixed J. Okay, so a key question is, we have a simple formula for the average over J of phi. And so the question is the average over phi of sigma, is this approximately equal to just phi itself for sort of typical values, typical but fixed values of J? So if we just pick out of a random number generator some set of these numbers J, we evaluate phi of sigma, is that approximately equal to the average over J? So this is, in the study of disordered systems, people call this, is the quantity self-averaging or not? Is it almost equal to its average over the couplings J? Because guess what? If it is approximately equal to the average, then we can just go back to the previous simple average theory, use our wormhole saddle points, and compute the answer and be done. So that's the question. And here's the strategy to try to answer it. The strategy to try to answer it is to compute the average of phi of sigma squared and the average of phi of sigma squared. So if the quantity is self-averaging, then these two expressions will be almost equal to each other. And if it is not self-averaging, then they will not be almost equal to each other. So we'll be able to figure out the answer to the first question by computing these two things and just comparing them, just comparing the answers we get. Okay. Are there any questions up to this point? And in particular, is it making sense how we're introducing these collective field variables with the fixed values of the couplings?
Yeah, so just a small comment. Isn't it obvious that it cannot be self-averaging, because precisely then it would mean that you don't have the factorization or something, right?
Right. So it's obvious that it cannot be self-averaging everywhere, but it could be self-averaging in some regions and not in others. And
so for some values of sigma, you mean? For some values of sigma.
Yeah. And the important question is whether it's self-averaging in the region of sigma where the wormhole solution is. So it could be that it's not self-averaging even in the region where the wormhole is. And that would mean that the wormhole has no meaning in the theory with fixed couplings. It would mean that the wormhole does not exist. It doesn't mean anything in the theory of fixed couplings, because the action is just completely different at the location where the wormhole would like to sit. Completely non-self-averaging. So there's a contentful question: is this thing self-averaging at the location of the wormhole saddle point?
Okay, I see.
Okay, so we just want to compute these two things. We want to compute this thing and this thing, and we've already computed the first one, because the average over phi is just sigma to the n. So the first thing is just equal to sigma to the 2n. Okay, so great, that computation is done. We just need to compute the second one. And you can compute this exactly. So here I've written a expression. You should take q equals 4 to be consistent with the formulas we've been using so far. And this is an exact expression for the average of phi squared of sigma. It depends on sigma because of this. Whoops, because of this sigma to the 2 to the 8 and 1 here. It's not a very convenient formula. So we can also get a little bit more insight by doing a saddle point evaluation of this thing at large n. So, okay, the saddle point evaluation of this thing is a little bit complicated because, well, what is phi? Phi is an integral over. Sorry to be scrolling around so much, but phi is an integral over psi left fermions and psi right fermions. So it kind of has two copies of the system in it. And when we compute phi squared, we need to have four copies of the system. So we need to have a left, a right, a left prime, and a right prime. And so we have collected fields, sigma and G, for each possible pairing. You can see some of those here, left, sigma left prime, sigma right prime, and so on. So these different variables appear. So we have a antisymmetric matrix of G and sigma variables, and we can write the action after averaging over the couplings, and you can evaluate this by saddle point. And there's two different types of saddle points. There's a saddle point where sigma left prime equals sigma right prime equals sigma left prime equals sigma right left prime equals 0. And for this type of saddle point, where all of the kind of prime unprimed variables are 0, then we get, as you can see from this computation, from this expression here, you get just sigma to the 2n. So from that saddle point, you get the answer. You get the answer for, what is that? That's equal to integral to average of phi squared. So the saddle point where all of these prime unprimed variables vanish just gives us the average of phi squared. So if that saddle point dominates, then it means that the phi is self-averaging. It means that average of phi squared is approximately equal to the square of the average of phi. And so that's the case if this saddle point dominates. But there is also another there are other saddle points where, but other saddles exist. Other saddles exist where these prime unprimed correlations are non-zero. And so it becomes a detailed question, which saddle point dominates? Is it the one where these prime unprimed variables are 0, or is it the other one? And the answer depends on sigma with no indices. So that's the argument of this function here, depends on sigma. And the relative importance of the first class of saddle point, or the second class of saddle point, depends on sigma. And okay, I'm not going to do the computation, but you can imagine doing the computation. This is a standard thing. And what we can do is we can plot out in the complex plane the region where the interchange of dominance occurs. And that's this kind of scalloped, funny shape. So this is the region that separates the part where the sigma prime equals 0 saddle points dominate, and the sigma prime not equal to 0 saddle points dominate. So out here we have self-averaging, and here we have non-self-averaging. So this is the way that you show the, this is the figure that we sketched in the beginning of the talk, and this is how you actually show it mathematically, by computing the average of phi squared and checking whether the self-averaging saddle point or the non-self-averaging saddle point dominates. And for some regions of sigma, the self-averaging saddle point dominates, and for other regions it doesn't. And the two regions are correspond to the interior and exterior of this kind of funny scallop-shaped region in the sigma plane. And it's kind of interesting that there's some order 1 value. Like, so suppose we're going out in this direction towards the wormhole saddle point. So here on the unit circle, these are the wormhole saddle points for sigma. So this is on the unit circle, the 4th roots of unity that we discussed before, shifted slightly because of the contour rotation. So these are the location of the wormhole saddle points. And so if we start at the origin, the function phi is not self-averaging. And at some order 1 value of sigma, it becomes self-averaging. And it looks, in principle, it could have been at the wormhole or outside the wormhole, but it just so happens that it starts becoming self-averaging before we get to the wormhole. at some sort of order 1 fraction of the way to the wormhole, and the wormhole saddle point is self-averaging. This is true when Q is equal to 4. So we have an integral over 4 where the action involves a product of 4 fermions. If it involves a product of 2 fermions, then it's no longer true. So it's kind of non-trivial. In the case where we integrate over just an action with just product of 2 fermions, it's like a SYK2, which is like a non-chaotic theory. It has a somewhat different kind of holographic dual. For that case, the wormhole is not self-averaging. It's not in the self-averaging region. It's just kind of in the border, the boundary between the self-averaging and non-self-averaging region. So that model is different. It just shows that it could have gone either way. And it just so happens that for the more interesting cases with Q bigger than 2, the wormhole is self-averaging. Okay. So let's see. So one point is that the wormhole survives. I'm not going to make this third point here. Basically, let's just discuss 2 points. The wormhole survives. And second point is that there's a new important integration region. Near sigma equals 0. So let's look at this function phi. So in the average over couplings, remember the average over couplings of phi was equal to sigma to the n. So it vanishes at the origin at sigma equals 0. So it vanishes. There's no interesting contribution there. But in the theory of fixed couplings, the value of phi is actually really large near the origin. It's a large value of phi. And in fact, the contribution in the non-average theory from close to the origin is of the same order of magnitude as the contribution of the wormhole saddle points. So an accurate computation must include both the wormhole saddle points and the integral near sigma equals 0. So a third point is that the integral, so the half wormhole, so we call this the half wormhole, the region near the origin. So the half wormhole plus the wormhole, wormholes give a good approximation. Give a good approximation for fixed couplings. So this is how you analyze this theory semi-classically. Large N with fixed couplings, you include the wormhole saddle points of the average theory, but you also have to include a new contribution of the origin, this half wormhole, and together the contribution of the origin and the wormhole saddle points give a good approximation to the exact answer for fixed couplings.
Can I ask something? So,
yeah, please.
So you're saying for Q equals to 2, that wormholes are like within this yellow region, and does this have any consequences for how they cancel, or like why is it important for Q equals to 4 that the wormholes are outside of this yellow region? In the end, they must both of the cases must have factorization restored, right? So how is it? Where is it important?
In both cases, you have factorization restored, but this is the statement that depends on having Q bigger than 2 and having the wormholes outside in the self-averaging region is the first statement, the fact that the wormholes survive. So let's imagine that. Let me draw the plot for Q equals 2. So in that case, if I remember right, we just have, I think, just 2 of these solutions, one here and one here, and the self-averaging region looks something like this. So the wormhole saddle points are on the boundary of the self-averaging region, and in particular, they're not self-averaging. They're not self-averaging. That means that the wormholes kind of don't survive in the non-self-average, in the fixed coupling theory, because the action as a function of sigma is not well approximated by the average action, so you don't have the same saddle point at that location. So the wormhole don't survive. The wormholes of the average theory just don't really mean anything in the non-average theory. So that's the statement that depends on this fact on Q being bigger than 2.
So then the half wormholes must like cancel within each other, or there's I don't know. There's maybe just no saddle points, and then there's nothing to cancel. Or
yeah, what happens in this case actually? So technically, what happens is that there's a zero mode that relates the kind of relates the wormholes and half wormholes all together. So it's some kind of big manifold that you have to integrate over. And the semi-classical approximation is no longer, there's a flat direction in the path integral. You have to kind of integrate over this whole region. You have to integrate over this whole region, and you can't approximate it by just a contribution of wormhole and half wormhole saddle points. It's a bigger, kind of more quantum integral that you have to do.
Okay, I was also wondering whether there's anything interesting that happens at like the infinite Q limit. Maybe this yellow region shrinks, or
let me try to remember. Does it, okay, question is, does it shrink? I don't remember. We can try to work it out.
Yeah, I'm just asking because at Q equals 2, well, I guess the wormholes are always in the unit circle, right? Because of the way it was derived.
Yes.
So it seems to be shrinking from Q equals 2 to Q equals 4. So that's why I'm asking whether it shrinks completely in the infinite Q limit.
Yeah, so let's see if we can work it out. Let's see at least what equation we would solve to work it out. So let me write this. X G minus 1 over Q, G to the Q. So we would take this equation and we would do a saddle point evaluation of this. So here I'm taking one of the left prime. Let's say we make just this variable non-zero, left prime times right prime. Then I think we would get this. We'd have 2 of these. Well, let me not worry about the factor of 2. We're just trying to see if it shrinks or not as a function of Q. So we would take this integral, this action, and we would look for a saddle point in G and in X. Now, let's first do the, I hope this is correct, but let's first do the G saddle point approximation. So we get the equations minus IX minus G to the Q minus 1 is equal to 0. And then we can substitute that in. So we're going to get at large Q, we're basically going to get, this is going to be minus X to the first power. So we have an action which is like this, minus X squared minus X to the first power. So the function is a function of X, and sigma has a limit as Q goes to infinity after integrating out G. And I think that means that this circle is going to approach a finite point as Q goes to infinity. So now we just have this theory, and we're going to look for saddle points of this theory where X is 0 or X is non-zero. And so this is X to some power like 1 plus 1 over Q. And so there's a saddle point at X equals 0. And there will be a saddle point at some value of X that's and I think the action will have a limit as Q goes to infinity. So I expect, I'm not 100% sure that I did this right, but I expect that the blue circle approaches a limiting value as Q goes to infinity. But I actually don't remember if that's true or not. Hopefully I haven't made a mistake.
Okay, thank you.
Okay. Okay. Yeah. Thank you for the questions. So, okay. So let's try to explain why we use the terminology half wormholes and why the different contributions contribute kind of at the same order. The ones at the origin and these wormholes, why do they contribute the same order? So, just first some notation. So we can think of the contributions to z squared here without averaging, so with fixed couplings. We think of those as the solid portions of these diagrams that I've drawn here. So these are the actual z squared that we have, the z left and z right. And these are some like extra, I'm not sure how to say it, some sort of extra phantom z left and z right prime, which will be helpful for a discussion that we'll have in a second. So let's imagine that we have these two physical copies and these two kind of phantom copies. And the wormhole solution corresponds to a pattern of correlation between the left and the right system. And the half wormholes correspond to a pattern of correlation between the left system and left prime, between the physical system and the kind of the phantom system. And you'll notice that there's no correlation in this half wormhole contribution between left and right. So the left-right correlation is 0. There's correlation to some other phantom system. And why do we call it a phantom system? Well, because let's imagine now that we compute actually z to the 4th. So we have 4 copies. And let's compute z to the 4th, the average of z to the 4th, by taking our previous computation of z squared with the phantom systems and averaging it over j. And now these phantom systems become the other factors of z left prime and z right prime in z to the 4th. And the wormhole contribution corresponds to just this one. It's the same in the two computations. And these other ones become actual wormholes connecting z left to z left prime or z left to z right prime. And so in the computation of z to the 4th, these 3 different patterns are related to each other by permutation symmetry. So they're equal to each other. And that means that the wormhole contribution, which is this one, wormhole contribution, has to be of the same order of magnitude. Sorry, I circled the wormhole in the wrong thing. That means that this wormhole contribution here has to be of the same order of magnitude as this half wormhole one, because when we square them and average, we get the same result. So these contributions are not self-averaging, but they have an RMS value, like a mean square value, square root of mean square value that is the same as the self-averaging wormhole contribution. And the way that you can show that is by squaring the whole thing and taking the average, and then you find that these 3 contributions contribute equally. So their square, the average of their squares is this are equal to each other, but 2 of them are not self-averaging. Those are the half wormhole contributions, and 1 of them is self-averaging. And you'll notice, just to repeat it again, sorry, what's happening here? Okay. You'll notice that these contributions, there is no correlation between left and right. That says that G and sigma are equal to 0 for these contributions. So that's like the origin here. That's the origin of the sigma plane here, with no correlation. And what is the correlation? The correlation is this left prime or left right prime correlation when we average. And in the theory where we don't average and we just have z squared instead of z to the 4th, it's like we have half of that. So concretely, the half wormhole contributions are supposed to be the left, so sort of the left and right components of the saddle points, of the wormhole saddle points where we double the number of systems. So that's the more precise definition of the half wormholes. Okay, so let me try to summarize what we discussed. So where do the wormholes come from, and how is factorization restored in this toy model? So first of all, where do the wormholes come from when we're computing z left times z right? Well, we introduce the left-right correlation through this integral. So this is the step where the wormholes get introduced. Is we write 1 as an integral over this variable g left right of a delta function and so on, and then we what do? We represent the delta function using an integral over sigma. So this is standard from studies of SYK. And then we approximate the resulting integral semi-classically at large N. And there are two types of contributions. Contributions A are the wormhole contributions in the self-averaging region. And then there are the half-wormholes in the non-self-averaging region. And since we've just done legal mathematical steps, we've introduced 1 equals this thing, we've represented this as an integral, then we've approximated the final integral semi-classically. Since we've done legal mathematical steps, this must give a good approximation to the product of partition functions in the non-average theory. So we've done only legal things, so we should get a good approximation. And that is actually, strangely enough, that logic there is actually the most efficient logic I know of to derive this approximate equation. So this is kind of the magic that makes factorization work. And it's not an obvious equation. And the most efficient derivation I know of is basically just that this procedure is mathematically correct. Like it's a correct procedure to approximate it. And the final answer must factorize. The final answer must factorize. And we've done legal steps. Therefore, the half-wormholes have to satisfy this equation. You can check it more directly. You can check it a little bit more directly, but not that much more directly. This is, in some sense, the most efficient demonstration of this identity. Okay, the last thing I want to tell you about is just because it relates to what we discussed last time is that you can consider a slight variant of this model of what we've been computing of z squared, which we'll call zeta of mu. And that's an integral over 2n fermions of the same stuff that we've had so far. It's the couplings times the left fermions and the right fermions. So this is what we've discussed so far. The new thing is that we include this term mu times psi left times psi right. So this is very much like the interaction between the two systems that set up the eternal traversable wormhole in Tuesday's lecture. So this Gauss-Jeffers wall interaction that sets up this Malacena-Chi eternal traversable wormhole, whatever, some interaction between the two systems that allows this wormhole solution to exist. And we can ask what that does in this case. What happens in this case if we introduce this term? And it's actually easy to see what will happen kind of using perturbation theory. So let's imagine that mu is very small. So this is going to introduce a term e to the mu times g left right. And so the effect of mu we can evaluate in first order perturbation theory by just taking the value of g left right at the saddle point and multiplying it by mu. So for the wormhole saddle point, g left right is non-zero and equal to a root of unity. So it's basically, this is something with the order 1. So if for the wormhole saddle point gets enhanced, so the wormhole is enhanced by, sorry, this is n times mu, by e to the n times mu for small mu. So at first order, the wormhole gets enhanced. The half-wormhole is a region where g left right and sigma left right are equal to 0. There's no correlation between the left and right systems. Is not enhanced. You can work it out to second order and you get e to the n times mu squared. So for small mu, the wormhole is enhanced by much more than the half wormhole. And so what that means is that if we look at this plane, we have these wormhole saddle points, and we have a half wormhole saddle point, And in the theory with mu equals 0, which is what we've discussed so far, these all contribute in kind of the same order. But when mu is non-zero, then the wormholes get enhanced, or more precisely, one of these wormholes gets enhanced, and the half wormhole does not get enhanced. So now a good semi-classical approximation to zeta with fixed couplings is just coming from the wormhole contribution. Just coming from the wormhole contribution. The half wormhole is subleading to the wormhole after turning on this coupling. And what that means is that zeta of mu is itself self-averaging. So zeta of mu is itself self-averaging. And so here we see that the kind of the wormhole is all you need in this case where the two systems are coupled by an explicit interaction. There's no contradiction with factorization because now the two systems are actually coupled with each other. So their partition function should not factorize. And the way that that arises is not because like the wormhole disappears or reappears, or the half wormhole disappears or reappears. They're always both there. It's just that when we introduce this coupling, the wormhole contribution gets enhanced a little bit above the half wormhole. And so it becomes a good approximation to only include the wormhole. And that's what happens when we turn on this mu. Okay, so that's it for this lecture, and I guess this is the end of the series. So thanks very much for your attention, for the questions, and I'd be happy to answer any more in the remaining minutes.
Okay, thank you very much. Well, so I did get my question answered. So I see what you mean, that this, okay, you can still indeed introduce these collective fields, and okay, and so that's okay for me. So
Okay.
If other people have questions, please, now is the good moment. Including questions, maybe conceptual, or, can go beyond the lectures. So
Yeah, for sure.
just the opportunity to ask Douglas whatever you want to ask.
Yeah.
I have a naive question about in your previous lecture. You had these wormholes that explained the ramp of the spectral form factor.
Yeah.
So, for instance, you could look at the spectral form factor of the SYK model. And I was wondering if you look at single realizations of SYK, do these same wormholes survive there? Like, are they also self-averaging?
We believe so, yes. We believe they are, but we're not 100% sure. So we made some comments about the SYK case in our paper, but we're not able to analyze it as reliably as for the single site model, mainly because it's harder to exclude the possibility of other saddle points. So we have an infinite dimensional integration space, and it's harder to exclude the possibility there could be some other saddle points that dominate over the ones that we know about. So of the ones that we kind of know about and that seem reasonable, if that is all there is, then yes, the ramp is wormhole is in the self-averaging region, but it's hard to prove that there are no other contributions. So basically, we think the answer is yes, but we don't know for sure.
Okay, so then the slope would be self-averaging in itself. The ramp is not self-averaging in SYK, but it would be controlled by some wormhole that you believe is probably self-averaging. Is that the situation?
It would be a wormhole that's self-averaging plus half wormholes that contribute the random. So this would be
right. Yes.
This would be some wormhole plus half wormholes. Would be this region. This region here is just two disks. And if we average this, so now let's see what happens if we average. If we average, this one goes away.
Right. Okay, thanks.
So, any other question?
Maybe I have a question. So you were speaking about SYK, but have you thought about maybe doing some, instead of in one site for the time, you have a number of discrete times and sending this limit of to infinity to have an idea? Did you think of this approach?
Yeah. Oops, I said it wrong. Let's see. So yeah, it's an interesting idea. So we could do the first step along the path that you suggested of taking the number of points to infinity. We could just take 2 points instead of 1 point in time, and that is actually this theory here. So this is 2 points in time, where we identify left and right with the 2 points in time. So this is the kinetic term, and for the fermions, so the fermions should have a psi dot psi term in the action. And this is a discrete approximation of that, where we just have 2 time points. And this is the SYK interaction evaluated the 2 time points. So if you like, this zeta is a case with 2 time points. And the saddle point analysis gets more complicated. Like this case is pretty manageable. But as you increase the number of time points, the number of variables that you have increases, and your ability to definitively exclude other kinds of saddle points is well, we didn't manage to do it. Maybe one can come up with an argument that there aren't.
Okay, thank you. Yeah, I see.
So I like this zeta because you can think about it. You can think about it either as SYK with 2 time points, or you can think about it as 2 separate systems with an interaction between them, like the Malda-Senecchi eternal traversable wormhole. So it's kind of a nice model for either of those 2 things. Yeah, but your idea is a good one, I think, of trying to sneak up on SYK by introducing more time points and just seeing, like, maybe at some finite number of points, like 3 points or something, maybe something goes wrong. That would be very interesting.
Okay, thank you.
I also had maybe a question related to last lecture.
Yeah,
if that's okay.
Yeah, please.
So, well, you were giving examples of wormhole geometries, but as far as I could tell, all the examples were with 2 different asymptotic regions. So
Yes.
I was wondering whether there exists examples which are more like the second type of pictures you were drawing, where you have one asymptotic region and then a wormhole connecting two regions in the same asymptotic
Yeah,
region.
so there's a paper by Saad. It's called Late Time something. I forget the whole name. It includes baby universes, late time correlated baby universes. And he computes the following thing. It's a very nice paper. He computes the 2-point function. Let me not write angle brackets because that's going to bias us towards ensembles, but O of t, O of 0, e to the minus beta h. So he computes the thermal 2-point function and the contribution to it coming from a geometry with the following topology. And so it's well known. So there's a paper, I forget if it's 2001 or 2002 or 2003, by Maldacena, Eternal Black Holes in Empty de Sitter Space, where he introduces this thing called Maldacena's information paradox. The paradox is that this thing on the black hole geometry goes to 0. But in quantum mechanics, it can't go to 0 at late times. So this is a tension between the black hole and quantum mechanics. And what Saad does in his paper is he analyzes the contribution to this 2-point function coming from the wormhole that I drew here. And there's a contribution where the kind of the geodesic connecting the 2 operators, or the correlation between the 2 operators, threads the wormhole, and that gives a non-decaying contribution. So this is a type of solution to the to that problem. So this gives a non-decaying contribution. And you can think about it as kind of this. These wormholes are tricky because it depends on, how you think about the wormhole depends on the coordinates that you use. But you could think about it as like a thing that connects the 2 points together. So like there's a non-decaying correlation between early times and late times because a wormhole can kind of connect the 2 points together and make a shortcut. And that's a physical interpretation for why the correlator does not decay. So that's an example of I think of what you were asking.
Okay, thank you.
Yeah, there was actually previous work. I cited Phil's paper here because it was the most precise computation of this, but actually there was a previous suggestion along these lines that had this idea. It was Blomer, Mertens, and Verschelde. So they had this picture, and I should cite that one as well. So Blomer, Mertens, and Verschelde, they both have these pictures, and I think their paper is called Clocks and Rods, or something like that. So you can look at both these papers. They're both very interesting.
I see, thanks.
Okay, so maybe I can add one question. Do you have, any idea about, the type of two-dimensional quantum gravity theory that could accommodate these half wormholes? You said that this, bizarre region of the half wormhole where we don't really know what it is, maybe it might be related to some black hole singularity. So that seems to exclude any model where you would fix the curvature, for example, like in JT, where all the geometries are fixed curvature, so you're not going to have any singularity there. So does it mean that we really have to enhance those models in a very non-trivial way to get those objects? Or
I think that's a really interesting question. Yeah, so like the theories of gravity that seem most firmly dual to ensembles are like JT gravity, let's say, which doesn't have a black hole singularity, or three-dimensional pure gravity, which also doesn't have a black hole singularity. So maybe this is not a coincidence, and maybe the absence of a singularity in these models is connected to the absence of half wormholes in these models, and is connected to the fact that they're actually dual to ensembles. And the theories with actual honest black hole singularities have new contributions where the wormholes can end on the singularity, and that in principle resolves resolves the factorization problem and allows these theories not to be dual to ensembles. So I'm sort of rephrasing your question. I think it's a very interesting possibility. I don't know if that's right, or if the role of the singularity is kind of a red herring. Okay, so it's more work for the future. Yeah, more work for the future. Yeah. Another possibility is that even in let's say in these two-dimensional models, maybe there's an effective description of the half wormholes where you just put a boundary condition, some kind of brain there that's like an effective description of the half wormholes, which allows you to avoid worrying about the singularity or whether there's really a singularity in this model. It could be that that's possible in any case.
Right. So you would have to add a new boundary that would appear dynamically, sort of, that you have to include those configurations in the path integration.
Yes. I think it's likely that is a valid, effective description. It might not be the correct fundamental description. We could imagine the correct fundamental description involves a singularity, somehow it's very complicated, uncomputable. And maybe there's a valid effective description that involves unknown data that you just have to input, which are the coefficients, like the weightings of the half wormholes. That's one possibility.
Okay. So any other question? Are you sure? Because it's your last chance. Otherwise, I think we can close the session and thank very warmly Douglas for this very insightful set of lectures. And we hope we'll have more, maybe later at some point.
Okay, well, thanks a lot. It was a pleasure for me, and it was nice to interact with you folks. And I hope to do more in the future. So thanks a lot.
Yeah, thanks a lot, Douglas.
Yeah. Thank you very much.